Zaynab, are you ready? Go for it.
Awesome, thank you. Hi everyone, my name is Zaynab. I will be introducing you, well, I mean, you've already been introduced to Big O, but I will be just giving a little lecture on Big O. A little about myself, I was born, kind of raised here in Chicago. I went to UIC and got my undergraduate degree from there in computer science. And I worked in the industry for a little bit, and now I'm here. But yeah, I will get started. Okay, can everyone see my screen?
Yes.
Thank you. Okay, so Big O notation. So before we fully start, what are some things when you're writing code that you really want to keep in mind?
Performance.
Performance is a very, very important one. So what about, definitely. Anything else?
Readability.
Yeah, definitely.
Reusability.
Yeah, I think you guys covered it all. So a lot of the important things are about code, like you said, the readability, reusability, but also the how much time it takes and how much space it takes is a very, very big important thing, especially with, you know, computer or programs run on servers, and servers have physical space that you need to take up. I know even the cloud itself is a physical server. So these are two important things. So what is time complexity? Could anyone tell me? If we're talking about a program's time complexity.
Amount of time it takes.
Yeah, it's just the amount of time it takes to run a program. What about the space complexity?
Amount of storage space it takes just
Yeah.
when the program runs.
Yep, exactly. How much working space you are required to use to run the program. So Big O notation, according to Wikipedia, is the mathematical notation that describes the limiting behavior of a function when the argument tends towards a particular value or infinity. Kind of wordy. So basically, it's a notation that we use to classify algorithms based on their time and space complexity as their input size grows. So we use it to describe how much space and how much time it takes to run in a worst case scenario. So let's say you have an algorithm and it takes an array as input, and you want to see how much time will that algorithm take relative to the array size. And the formal definition of Big O is the function f is O of g of n if and only if f of n is less than or equal to c times g of n for all positive values, pretty much. That's what it's saying. And this doesn't really make sense when you first glance at it, but I'll give an example and we'll come back to this in a bit. So let's say we have this algorithm and we want to compute the time complexity for it. So what is the time complexity for this, if anyone would know? So we have one instruction and it is looping 5 times.
O of n.
So for here, we have an actual value. So we know that it's only looping for 5 times. So regardless of what your input is, it doesn't really matter. It's always going to run 5 times. So for this one, it's O of 5, which is a constant number. For the next one would be, we just said the answer. So that one would be O of n, because we are looping through an array, and the array would be size of n. So we don't really know what the array length is yet. So this one would be O of n. This second loop is also the same, so O of n. And these three instructions are just going to be O of 3. So pretty much to find the complexity, you just add them up. So if they're in succession, you add them. If they're inside of a loop, you multiply. So here we had 1, and the loop was going on for 5 times. So it's 1 times 5. That's pretty much the way to do it. So here we have our actual function. So if we simplified the terms, we just get O of 8 plus O of 2 of n. And when we're using this notation, we really don't care about the constants. So you will end up with O of n just by itself, because we don't care about the constant next to the n, and we don't care about the O of 8. So if we bring it back to here, this is our definition from before. So if you see f of n is 8 plus 2n, and then g of n is just n. So if you multiply g of n by a certain constant that is positive, you should get something that is equal to or greater than f of n, which if we multiplied it by 3, we would probably take care of that, because we have 2n. If we add 1 more n, if n is greater than 8. If not, you can multiply it by 20n, and you'll have a value greater than that. That's pretty much all that this formal definition means. Any questions yet? Okay. So other variations of these notations are, so we just talked about big O, which is the upper bound. So this is the most amount of time or most space that an algorithm would take. Omega would be our lower bound, so the least amount of time. Theta would be exact, and little o would be upper bound excluding exact bound. Usually during interviews, people don't care much about like omega, theta, that stuff. Sometimes they want like an exact bound. So maybe, yeah, they might say big O, but they mean big theta. So sometimes just knowing the distinction, just mentioning it would be fine. Yeah. So some of the forms that you can have inside of the parentheses are any of these. So they're all a form of a variation of n, something with log, n, 2 to the n, 2 to the something, n to the something. But yeah, so it could be any of these, and there's a lot of different ones, and a lot of more complex ones when you're computing mathematically. But for programming's sake, you don't need a lot. It's a lot of like proof stuff that would need these. So these are the main ones that you're going to probably come across. So O of 1, constant time, usually just means an instruction. So you don't really care about how big your input is, because you're not really using it. You're not really using like the entire input. So you don't care how big it is. It's not always 1, but because it's a constant, we just say O of 1. We don't really care. We have log, we have linear, we have, so O of n, we have n log n, which some people call quasi-linear or log linear. We have quadratic, cubic, exponential and factorial. So just to see how they compare. So if n is equal to 10, this is how it progresses. So you have your constant log linear. The numbers are still, relatively okay. Even quadratic seems fine. 100 instructions, that's not too bad. Goes up to 1,000 here, and then n factorial goes up to over 3 million. And this is just for a size of 10. So if you go to 20, if you just double it, you notice log stays pretty low. Linear just is linear, so it works in accordance with like this, just the regular slope. So it increases as the value increases. Log linear, it's literally just the multiplication of so n times log n. So it's going to be higher. And yeah, so here you also notice that the factorial is getting very, very high. And even the exponential, it's getting up there. It's up to 1 million now. Then when we go up to 100, you see that up to like quadratic, this is okay. Cubic is kind of fine, but here, this is where you're gonna have issues, because if you're this is running in seconds, you're gonna have your program running for days, maybe. So this is why we kind of care. We don't really want exponential, factorial, even polynomial, what is it called? Complexities. We want to try to reduce it as much as we can. Any questions before we move on? Okay. So also feel free to stop me at any time if you do have any questions. So as we said, an example of constant time is just any instruction. So here, even though we use the array, we use some parts of the array, we're only accessing 2 elements. And we don't really, so if the array is size 10 or 10 million, it doesn't matter. It's going to be constant. An example of log would be binary search. I'm not really sure if, have you guys been introduced to binary search or?
Yeah, we have somewhat.
Yeah, okay. So I won't go too much into detail then, but binary search, basically you have a sorted array that you want to search, and what it basically does is you take the entire array, you find the middle, and then you see if the value at the middle is, if it's equal to the value that you're looking for, you're good, you found it. If it's more than the value that you're looking for, so the value is going to be on the left side, you disregard looking in the right side, so you just now take the left side as your new array bounds, and you keep doing that until you find your value. So it's log of n because it pretty much cuts it in half every single time. And this is just a little animation of what it is. So it's looking for 37 and it keeps cutting it down until it finds the value, versus a sequential search, it just keeps going one right after the other. And even in the worst case scenario, you're like for 17 values, you're not going to go for more than 4 steps, which is log of 17. So yeah, it's a pretty good program, or pretty good time complexity. We like log n. So an example of a linear time complexity or space complexity is this. So just a simple loop in the array. So you loop for every single number, you do something, and that's it. So if this grows, then the amount of instructions grows. So if we have this, we have an array up here and then another array down here. We'll see, like these are the same array, so the same size. What would be the time complexity for this one?
O of n.
Yeah, because we add this is O of n, this is O of n, we add them together, we disregard the 2 because we don't care about it, and yeah, it's O of n. What about space complexity? So space complexity is how much space we're really taking up in this. So
Would it be the, never mind.
no, what were you gonna say?
I was thinking along the lines of whatever the space of an integer is times the number of integers in the array, but then I'm like, well, the array is a different data type, so it probably has a different memory signature or amount.
So you're on the right track, but so for here, we're only keeping track of 2 integers actually. So we have the sum and we have count because that's the only thing that we're adding to. So we're in the space wise, there's the array, but we're not adding any working memory to it. So the space would be constant. It's just O of 1. Any questions?
It wouldn't be O of 2 since there's 2 different variables, sum and count.
Yes, technically it would be, but with constant, it's always going to be O of 1.
So it simplifies down to O of 1.
Yeah, everyone just says O of 1. Yeah. Okay. So the next one is O n log n. So can someone tell me why this is n log n? Okay.
You've taught us that. Oh, go ahead.
No, I was just saying it's because it's a loop with a value based on the array, but this actual loop is based off the binary search, which you kind of had just laid out that based on binary search, that's interpreted as O n log n. So I guess I'm saying that it's depending on the binary search. So you would default to that value.
Okay. Close. So actually the binary search is just log n. The n is coming from the loop itself. So we're looping the entire array, but then for every single item in the array, we're doing a binary search, which is log n. So that's why we're multiplying it since it's inside the loop. Yeah. Oh, well, I gave the answers here. I forgot to. But yes, so this is kind of similar to the one before, but the binary search is above it. I just wanted to point out that when it's not inside of the loop, you're adding it. So this is log n plus n. And since n is larger, you are just going to take n. You're not going to take log n at all. So time complexity, O of n. And then can someone tell me why the space complexity is O of n here? So what this code is doing is, this one is just doing a binary search on an array to find the value 5. And this loop is going through the array, and then this is a new array. We are appending a new value to the array. So we go through the array and then we add the value that we found. and we append it to our new R array. So why is the space complexity O of n?
Is it because the array that we're basing this all off of is constant?
No, it's because what is it called? You're creating a new array here, and that is what's like taking up more space. So, and this array is going to be the same exact size of your original array. So we create a new array as a result with size n. So the space complexity becomes O of n. Any questions? Okay. On to the next one. So another example of n log n is merge sort. So it is a type of sort that is relatively quick. There's also quick sort, which is a little quicker, but I'll talk about that one later. But yes, so merge sort, you take an array and then you split it in two, and then split it, and then split it. So you keep splitting it in half until you get singular digits. And then with these digits, you merge them while putting them in order. So here we have 38 and 7, 27. 27 goes first, and then 38. And same for here, same for here, same for here. And then it does another merge. And then it merges these two together. So yeah, 3, 27, and so on. So the reason why this is n log n is because you are, so this part would have been like, if you're just remember the search before, the log n, you're just kind of traversing through like one of the branches. So you're only going log n times down, which when you do like a binary tree, you end up, the height of the tree is like 2 to the power of, is log n of the, what is it called? The amount of nodes. So for here, you have to go through every single item, the amount times, what is it called? Log. So log n here would be 3, 1, 2, 3. And you are going through n times those times. So each row you're going through n items. This row you're going through n items, and this row you're also going through n items, just to make sure that it's all correct. So yeah, that actually I believe it's 2, not 3, but regardless, so merge sort is a good example of n log n. So we have a quadratic one, so n squared. And based on what we were talking before, so we have a loop through all the items, so that's n. And then inside of it, we have to multiply with something else, is another loop with size n. So it's n times n, which is n squared. And that's it. That's what we get for this one. So what would the space complexity be for this one? Did I lose you guys on the previous example?
Would it be O of n again?
O of n. So pay attention a little to the double loops. So if we have an array of 4, let's say, so we're looping through 4 items, and then for each of those items, we're looping 4 times again. So it's going to be 16 turns altogether, because for item 1, we have 4 loops, and then 2, 4 loops. And then, so we have altogether.
Quadratic,
Sorry?
is it quadratic?
It is quadratic, yeah. So it's going to be n squared. I didn't write it down here. But yeah, the space complexity is n squared because since you're looping twice, you have n times n, what is it called? Times that you are appending to this new list. So you're creating a list that is, what is it called? To the second power of whatever your original list was. So if your first list was 4, your final list is 16. Okay. So what about this one? Time and space. What's the time complexity?
I'm gonna guess exponential because it's one of the bad ones.
Okay, why?
Well, you've got 3 loops within each other, and it's gonna take it's gonna like multiply.
Mhm.
And I remember from your example that exponential is one of the ones we're supposed to avoid.
Mhm. Okay, so exponential would be, so the equation for that one would be like 2 to the n, which is, so for here, we have an n over here, right? So n, there's another loop inside of it times n, and then there's another loop inside of it times another n. So n times n would be n cubed. So your time complexity for this one is actually going to be n cubed. And the space complexity will also be the same. So yeah, kind of similar to this one over here. We just added another loop, so you're adding another power of like another degree to your n. Questions?
I've actually got a general question.
Mhm.
I can understand how this is helpful for like a junior developer to basically avoid as much as possible nested loops. I don't imagine in most of our jobs we're going to be responsible for like refactoring for optimal time and space complexities. So the question, if I can remember what it was, yeah, I kind of forgot it. Sorry. I guess you could comment on that maybe.
Yeah. So you might not be refactoring your code if you're working on stuff, but you will be producing new code, and let's say your first iteration of a solution needs 3 loops. You're gonna realize that like if you're writing some website for something and the lists are very, very long, and you have these 3 nested loops, you then realize that, okay, this is very, very slow. The page is not loading within like 3 seconds or whatever. It's loading within like a minute. So you end up having to figure out what to do. So this does help knowing where the issue might come from your code. So if you notice that your code is a little slow, this will help you identify like what might need a little more work or what might need refactoring and stuff like that. Yeah.
Makes sense.
Any other questions? Okay, so this is an example of the exponential one, which is indeed a pretty bad one. So hopefully you guys have heard of the Fibonacci sequence. If not, it's I actually don't know how to explain it. It's a list of prime numbers, I believe, if I'm not mistaken. That can't be divisible by can only be divisible by the two numbers that multiply into them, if I'm not mistaken. Could be wrong.
It's the sum of the preceding numbers.
Okay, so it is just this. Okay. Ah, thank you. It's been a while since I've worked with them, but finding the Fibonacci number of a certain integer, what it's called, is one of the examples of an exponential problem. So in this code, you enter a number. So you can enter, let's say 9. And what it will do is give you the number at the 9th index of the Fibonacci sequence. So what it does, or let's say we enter 5 in here, right? So your first call for 5 is going to do 2 calls to the Fibonacci function again. So this is a recursive function. So yeah, so 5 calls for fib 4 and fib 3, and then the Fibonacci 4 calls for 3 and 2 accordingly, because every time we're doing n-1 plus n-2. So for this one, it is okay, trying to figure out what the best way to relay this. So we have here 1 level, 2, 3, and 4 of how many calls we're doing. So on level 1, it's 2, and then level 2, it's 4. And then here it's 7, but, or sorry, 1, 2, 3, 4, 5, 6. Yeah, 6, but if this one had done a call again, it would be 8. So if you're noticing a pattern, it's kind of like a binary tree, where you have your first layer is, this one is 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, number of elements on that row. So this third row, 2 to the 3 elements would be 8. So you would have 8 numbers here, which there could be, right? Because there's 2 missing. But anyways, basically this is 2 to the n-1, because every time you do a call, you are adding 2 more, and you are multiplying, you're adding 2 more calls, and each of those calls then multiplies into 2 more calls. So that would lead to 2 to the n, but we always take out, so there's always an n-1 and an n-2. So that kind of factors into the n-1. But because we want to remove constants, it's going to be O to 2 of the O of 2 to the n. Can't talk anymore. But yeah, I know this is a little kind of confusing, but yeah, the Fibonacci function is an exponential one. Okay, and then so n factorial, which is one of the worst, or maybe the worst, is this could be represented in this tiny function. So what we're doing is, this is just the base case. If n equals 0, then we just print something. If n is not 0, so if we have a number, then for every number within that, so if we have a 5, number 5, it would be from 0 to 4 call this function again with f minus 1, so with 4. So at the first iteration, call f4, at the second iteration, call f4, and keep going. And then it calls, and then, so each time you're multiplying by n minus 1, or n minus the next iteration. So what this will look like if you put out like a tree of the calls, you start out with n values, and then you're multiplying it by n minus 1, and then you're multiplying it by n minus 2, and then it keeps going until you get to 0, and then this prints out. So yeah, that's pretty much a good representation of n factorial, which is just that. It's each number times the number preceding until you get to 1. Any questions on that? Or the one before, anything? Okay. So this is a helpful chart to kind of show where these complexities lie. So like we saw before, O of 1 and O log of n are pretty good. They're great actually. They run well, they run quickly. O of n, not optimal, but not too bad. O and log of n is also it's pretty bad, but it's not impossible. It's not very like, it's not horrible. So a lot of sorting algorithms. So if you're sorting lists, your complexity would be an n log n complexity. And then you have the horrible ones, which are quadratic, any polynomial. So 2 to the whatever number you have lies within here. And then your exponential is 2 to the n, it just shoots right up. And then n factorial, which is even a steeper incline. So there's also this website that I have come across. And it also kind of shows you different data structures and how their time complexity and space complexity show, or like how they perform. So this is a pretty helpful one. And these are sorting algorithms. So quicksort, I mentioned it earlier, has an average and best case scenario of n log n, but a worst case scenario of n squared. So it's actually interesting because quicksort, when it's being tested against merge sort, it is faster, because the worst case scenario is so it's so low, it's very rare, that a lot of people classify it as big O of n log n. So yeah, that's just an interesting fact that I found out. But yeah, how are we doing on time? Okay, went through those pretty quickly. So I actually had some code that I had written. I took screenshots of the values in case I didn't have time to really show, but so can you guys see my Visual Studio, my code?
No,
No, I can only see your browser window.
Okay, let me switch it real quick. How about now?
Yeah.
Okay. So I pretty much just had all the functions. You don't really need to care about the functions themselves, but I have all the functions from the slides that I mentioned. So constant, linear, quadratic, all that stuff. And I did some test cases to run it against. So we have, let's run these three. So we have our constant log, log of n, and then linear. And I'm running it against these values. So just, increasing the big. And this is size of n, by the way. So for each function, I was putting in an array of that size. So, okay, well, okay. So for O of 1, they're all less than a second. So I actually added a second to the time because anything less than 0, or a lot of things that are less than 0, it'll just show as a 0. It won't really show the speed because it's kind of negligible. So you see for the constant time, even like no matter how big the array got, the speed was pretty much around the same. So then we have for log of n. Also, is the screen too small or, oh, there we go. Sorry. So for log of n, it also kind of seems to behave like the constant a little bit. The numbers actually go up and go down, which is behavior I kind of noticed. When it's less than a second, it usually is like it differs. It's just based on a lot of different factors in your computer. So yeah, log of n looks pretty good. O of n, we noticed that here, when it got to the later ones, so here it went up to 2.7, here it went up to 34 seconds. So O of n is not really that ideal when you're getting up to higher higher numbers. Is it still there? No, okay. Okay. Let me run this one and so this is n log n, and I ran it against this. I couldn't even go up to, what is this number? I couldn't go up to 10 million. I had to cut it off at 5 million because it was taking way too long, which is also taking pretty long right now. I don't think it ran actually. Okay, well, for time's sake, I'm not sure if we're late on time, but okay, so these are the printed results. So n log n, we noticed it was pretty okay.
All right, are you sharing your other screen?
I am. Oh, it's not sharing. Thank you. I do not like Zoom that much.
Yeah, switching between windows is rough.
There we go. Okay,
Yeah, that's good.
perfect. Okay. There we go. So yeah, for n log n, we noticed that it was also pretty okay, and then it started getting a little higher, and then it got up to like 32 seconds over here. And like I said before, I had to decrease the amount from here because it was just taking way too long for the 10 million. And then when I went up to n squared, I had to decrease it to 10,000 because I mean, this is not that high, but the amount of time it was taking for the next multiple, so I just added a 0, and it was taking way too long, so I stopped it there. But if you can see, it got higher faster than the rest. Then n squared, I was only able to go up to like 30, I think, before it took more than more than 20 seconds. So yeah, so up to 40, got to 27, and then here I got only up to 9, and it was already up to 98 for the n factorial. So it was just a little interesting to see how fast these different complexities get to like a higher speed or a higher amount of time that they took. Yeah, that's kind of all I had. Does anyone have any questions or comments, concerns?
I kind of remember what my question was from earlier, so I guess I'll throw it out there.
Yeah.
I was looking at the like multiple for loops you had nested, and I was thinking, is there an obvious solution for that kind of problem, or is it really context specific to what you're trying to do in the code?
A lot of times it is specific. So sometimes there are like built-in functions into the language that perform better than like just looping through. So you might want to use that. So if you're like sorting a list and doing something else and doing something else, you might want to use some of those. I think just not nesting them if you can. So if you, because we saw earlier, if you just have the loops one right after the other, it's this, what is it called? The complexity is not cubic. It's not to the third, it's just n. So yeah, I think just the nesting is it depends on the what is it called, on the case. Yeah. Unless Tom, you disagree.
So I actually use Tom's Zoom for
Okay,
the.
I figured.
That's fine. Yeah.
I
Yeah. So it does depend. So a lot of times changing something from, let's say, O of n squared to O of n requires a different, like an entirely different approach to the problem. Sometimes using a different data structure or things like that. So we'll look at a couple examples. So there's kind of a subset of problems that there's a kind of 1 or 2 tricks you can use, but a lot of times it's just it's not obvious how you would do that. You have to think about the problem in a different way.
Okay.
Any other questions?
All right, cool. Well, thank you very much, Zaynab. Yeah, it was a great presentation of O of n. So yeah, we'll talk about that more as we do the algorithms.
Awesome. Thank you so much. Thank you everyone for having me, and thank you for the participation.
All right.
Awesome. Thank you.
Have a good one.